Well, thanks everybody for coming. Real quick, I have to say thank you to my mom also for all her support over the years. So my mom, Sharon, thank you. And when my 12-year-old son heard this was going to be on TV, he wanted me to wear a t-shirt with his picture on it. I'm sorry, just have to settle for High Da Vinci. But I noticed when I started teaching statistics that there was a difference between a statistics class and a calculus class is if you are in a calculus class, you notice that the history of calculus is kind of interwoven into the lesson. So you can't really take a calculus class without hearing of Isaac Newton. They're learning a little bit about Isaac Newton. But you can definitely take a couple statistics classes without really hearing anything at all about Ronald Fisher. And Ronald Fisher is sort of like the Isaac Newton of statistics. So I wanted to today talk a little bit about the history of statistics, some of the applications of statistics, and at the end show you an example that easily explains what a p-value is. A p-value is kind of an important topic, so that's the goal for today. I've got my notes here because my memory is not so good. But first we're going to look at an example of why to even study statistics. So it's a really easy example. Let's say we've got a really tiny store here. We've got 7 employees at S-Mart, and we've got their annual wages, and the employees go on a strike. And they apparently have the smallest union also. And the local media asks, what the average pay is, and we get a couple results. So the union rep says the average pay is $30,000 a year. The business owner says the average pay is $50,000 a year. And the question is someone lying? So if you have taken any math at all at some point or another, you probably learn probably at least 3 measures of center or words that mean the average. So the 3 most common ones all start with an M. What are the 3 you always hear? Mean, median, and mode. So real quick, how do you find the mean? Somebody just remind us. Yep.
Add them all together and divide them by the number of values you have.
Okay. What about the median? One in the middle if they're in order. What about the mode? Okay. So here's your first assignment. What I need you to do is on your sheet, write mean equals, median equals, mode equals. And I'll help you out a little bit. This, if you add these up, it's 350. So just want to take a second and find the mean, median, and mode. And when you get it, you have to do this one. When you get it, I need you to, this will be a tiny bit awkward because you don't know each other, but can you check with whoever you're next to and see if they get the same thing as you? And just so I see where we're at, if you got the same thing as the person next to you, can you just raise your hand a second? Or even give them a high five. Okay. Okay, so about 30%. So what's happening here? Are they both telling the truth?
Yeah.
So they're both using the word average, right? 2 completely different numbers. So what's happening? Why does 30,000? What are they using? Yeah, probably the median, right? When the government issues numbers that have to do with wages or housing prices, they always use the median for a reason, because as you can see, the mode here, or the mean, is heavily influenced by this, right? So these are both true, but maybe this one's a little bit misleading, right? So this is just a really easy example. Most examples are not quite as obvious as this, but even with the word average, if anybody's selling a product or an idea and they use the word average, on Wikipedia, there are 14 different versions of average, 14 different ways to calculate it. Even in our class, in our first year stats class, we look at 4 different kinds of averages. So you have to be careful with certain things. Average is just this really easy example. Most of them are a lot more subtle. So just kind of an example of just statistics helps just be prepared for things that we hear and read. Another example, we have, in our class, we've studied design of experiments. And it's a really important idea. And if you are a statistics major, you'll take an entire class on design of experiments. But we covered it in one section, so it's a real quick section. And if you apply design of experiments to medicine, or you have a clinical study, you basically will have, you have to see if your treatment beats a control group. So you have people that are very similar in a lot of ways. You randomly assign them to two groups. You get the treatment group, the control group. The treatment group is going to get some kind of treatment. The control group is going to get a placebo, but it's going to look just like the treatment group. I mean, there won't be a way to tell it apart. So if it's a blind study, that means these people, the subjects won't know which one they get. It's a blind study. If it's a double-blind study, then the researcher or the tester who's testing them also doesn't know which group they're in. It's a double-blind study. And it's good for eliminating bias. So what we do is we talk about that, and then I'm going to show you an example of something that maybe won't pass a double-blind study. So we've got homeopathic sleeping pills. So the way this works is kind of got a couple weird principles. One principle is like cures like. So for instance, if you can't sleep at night, you have a lot of energy, the idea is, well, it's kind of like if you had too much caffeine. So like cures like, so take some caffeine and it will help you sleep. Right? So kind of a weird idea, but then you can't just take caffeine, it has to be diluted a lot. So the other principle is that dilution will increase the potency. So what we have to do is we take, for instance, you take a drop of, let's say, pure caffeine, like caffeine product. You put it in 99 drops of water, and you shake it a certain way. So that would give you what's called a 1C mixture, a 1 centesimal mixture. So 1 drop caffeine, 99 drops water. And then you take a drop out of that, and you put that into 99 drops of water. That gives you 1/100th of 1/100th, so that's a 2C mixture. So what I have right here is a 30C mixture. This level of dilution is really extraordinary because just to think of the good old days in algebra class. You had 1 to the 100 to the 30th power. Just to make the math a little simple, I'm going to write 100 is 10 squared. And then you know this 30 is just a shortcut for repeatedly multiplying. If you take 30 of these, line them all up and multiply them together, you get 1 to the 30th, 10 squared to the 30th, which is 1 over 10 to the 60th. So this has a mixture of 1 to 10 to the 60th. So what we have to think about is, what does that mean? 10 to the 60th drops. How much water is 10 to the 60th drops of water? So if you have a lot of time on your hands over the weekends and you love doing unit analysis, you could say, hey, I wonder how many drops of water are in Lake Michigan. I hate to reveal this part of my life, but I did have enough time. And I found out that in Lake Michigan, there are 9.8 times 10 to the 19 drops of water, which is far too concentrated. I need 10 to the 60th. So I thought, well, what about all the Great Lakes? Well, 10 to the 20th, still way too concentrated. So luckily I had a lot of time that weekend. I said, what about the Atlantic Ocean? 10 to the 24 drops of water in the Atlantic Ocean, which means it's way too concentrated. So if I paddled out to the middle of the Atlantic, took my 1 drop of caffeine, mixed it up real good in the whole ocean, came back later, and took my eyedropper and dropped out 1 drop of water, what are the chances I would have any molecules of the original mixture, do you think? Pretty slim, but I'm still way too concentrated. So put all the oceans involved. I need to get here. I'm only here. So I thought, what if the whole Earth were full of water? That's still only 10 to 20. It's way too concentrated. If I went out in the middle of the Earth and put that in there and mix it around, it's still way too concentrated. So a sun-sized sphere, I'm just not getting anywhere fast. Here's a question for you guys. 1,000, that's 10 to what power? 10 cubed. Here's a quick quiz question. How many drops of water in 1,000? 2.8 times 10 to the 35th. You guys are good at this. So what this means is that basically I should be able to open this whole thing up, all of these. The like cures like already goes against everything we know about physics, chemistry, pharmacology. And now if you guys can just verify the math so I don't do anything dangerous. This is 16 times recommended dosage. So as long as our math is good, I should be able to eat all of these. Now remember, don't do this with real sleeping pills. And by real, I mean ones that pass the double-blind test. But this should be, is this right? Somebody verify? Okay. So I should be able to do this. They don't taste very good, but putting my life on the line for your statistics education. So, okay, we'll see how this goes. We're going to talk a little bit about the history of statistics, and these posters are right over there. So when you leave, for putting up with me today, you can take one of those. As long as you agree to hang it on your wall and look at it for 5 minutes every day, and you can take one. But when you do get that, look at the year 2008. You'll be very glad to know what happened in 2008. So you don't want to write that one down. So statistics, it turns out, is a very new field. So I just want to compare it to some other fields. Ever hear of this one? Been around for a long time. About 5,000 years ago, the Egyptians were using geometry for surveying, construction, astronomy, working with angles and lengths and areas, things like that. And you may have heard of this book. Hopefully you have. Even that, 300 BC, The Elements was published, and it's considered the most influential textbook ever written. It's been, according to, Carl Boyer, this book has had, there's only one book that has more editions published than The Elements. Only one book on the planet. That's the one. This is the second most. It's got over 1,000. Now at Stewart, we're at number 8, the 8th edition of Calc 1, so got a ways to go. So geometry's been around a very long time. So then I was going to compare to algebra. And again, it's hard to do these justice. I'm just taking little clips just to make the point these are old. They've been around a long time. Babylonian mathematics. You guys may have heard of the Plimpton 322 tablet. These numbers over here are Pythagorean triples. A squared plus b squared equals c squared. You get things like 3, 4, 5, 5, 12, 13, which means they were using quadratics back then, and also cubics. Then we have Al-Khwarizmi. This book's kind of a mouthful, but if you look at one word, what does that kind of look like? It's a little bit like algebra, right? So if you write this in English, it's still kind of a mouthful, but it even sounds kind of like algebra, right? Completing balancing with equations. Of course, this one was written in words, so if you open it, I imagine it would look more like a novel. Even if you had the number 16, it didn't say number 16, it wrote out the number 16. So still a little different than what we're used to. And then modern algebra began late 1500s, and then we started having the symbolic algebra that we're used to. But the point is, both of them been around a long time. So then we have calculus. Who's in calculus right now? Okay, got a few. So this one, Archimedes wasn't the first, but he developed at a pretty high level this method of exhaustion, which is a little bit like a precursor to integral calculus. But then not a lot happened for a while. In the 1600s, a lot of little pieces started getting put together. We had the fundamental theorem of calculus with Newton and Leibniz. 1700s, people started using calculus a lot. And then in the 1800s, everything started getting, all the pieces started to get put a little tighter together. There's a lot more rigor introduced, careful definitions. This particular one, this is from a paper written by Weierstrass, who was my favorite mathematician. And this is a definition that started from Newton, and then Cauchy tightened it up a little bit, and Weierstrass just changed it a little bit. And if you look at this definition, this is from about 1850. If you are a calculus student and you look in Stewart's book where it says precise definition of a limit, or any calc book that says delta epsilon definition of a limit, that's essentially it. It really hasn't changed since 1850. You might be thinking, I know there's a newer edition of Stewart coming out, but to save the suspense, I'm pretty sure it's not going to change in that one either. So, been around for a while. And then we have the beginning of statistics, much, much newer. There was a book that came out in 1662. John Grant looked at the mortality rolls in London and used it to give the first statistical approach to figuring out the population of London. And that's when some people kind of date the beginning of statistics to here, but it was mainly just recording things. It was governments used these for demographic data, economic data, and really to figure out who they could tax and how much. That's really what it was for at this point. But he had the first life table. And you may notice that this is a little bit of a depressing life table. You can actually see this book online. That's where I got this information from. There's a PDF of it. But basically, during this time, this is before the plague, in case you're wondering. The plague came out like 1665 and 1666. But this is just kind of the history of human beings up until modern times. Out of 100 people who were born, 36 would be dead before the age of 6. 60 would be dead before the age of 16. So kind of a scary time to be a kid, which it always was, just because there was, you couldn't always get clean water. Even things like penicillin didn't come out until the late 40s. We have vaccines now, so now you never really worry about smallpox, polio, mumps, rubella, things like that. But you used to worry about those all the time. So during this period, just to show the contrast, one person would typically make it to 76 out of 100. If you look at the modern life table, somebody take a guess. What do you think this would be? It's about 66 now, 66. So times are much better. It looks completely different now. Life expectancy in the U.S. in the year 1900. 1900, what was it? Anybody know? Yeah, depending on the source, most of them will say about 47. Right now, the life expectancy is 79. But here's what you can do. To see where we're at today, things are not quite as depressing. If you look for your age in this first column, does everybody have one of these? Then look in the last column. That's how many years you would expect to live from now, on average, if you're an average person. So once you get your number, I've got bad news for some of you and good news for some of you. And that's because this is aggregate data. So guys, when you get your number, here's the bad news. You can knock off 1 or 2 of those years. But ladies, good news. When you get your number, add on 1 or 2 years. But definitely less depressing than the older life tables. These are much happier tables today. So it turns out there are a certain group of people who use these tables all the time. And according to a lot of surveys, these people love their job. I don't want to give this away completely, but these people, this job, it starts with an A and it rhymes with actuaries. You know? You're right. It was too much, right? Actuaries. Sometimes my students ask me about actuaries, and I used to know some actuaries, and I lost contact. So when I knew I was going to do this talk, I got a hold of a friend of mine that I haven't seen in a while who is an actuary. But I just wanted to tell you about it. If you like statistics, or if you like math in general, you like solving problems, you don't mind using a computer, these are really, apparently from all the surveys, people who have this job really seem to like this job. So whenever they have like a job satisfaction survey, if you look on there, you're almost guaranteed to see actuaries, often at the very top. So sometimes my students ask me about this, and so here's some information. This is a good spot for information right here, beanactuary.org. If you like solving problems, you know, and you're just curious at all about that job, that link, it's put on by the Society of Actuaries, and I think, well, there's one other one that works on that. But so there's some good information there, and also I can tell you if most of the actuary jobs in Michigan are either in Lansing or in Detroit. And I got a hold of that friend of mine. He worked for quite a while at Blue Cross and Blue Shield of Michigan in Detroit. He's now working for a firm in Boston, but he gave me his email. And I got a hold of him because in grad school he's a really good teacher, so I knew he'd be one to talk to. And he said he'd be glad to talk to anybody who has any questions. So if you want to get his email, just talk to me and I'll give you his email. But anyway, it's something I always just wanted some of my students to be aware of. I think they might be interested in that field. So now we can talk about statistics. So it's a new field, like I said. Before you understand statistics, you have to kind of understand probability. And probability, these pieces started to get put together in the 1650s, and a lot of it was from, the questions were from gambling, dice games, card games, and there were some gamblers who were asking mathematicians questions. And if you know any mathematicians, you know what happens when you ask a mathematician a question, right? The answer starts and it just doesn't stop. They just keep on going, and so all of a sudden, here's probability. All these little pieces were getting put together. So let's see, so that started then. Modern statistics is actually really modern. Most people will date modern statistics to late 1800s. And a lot of people will say in 1890 when Carl Pearson kind of showed up on the scene, and he put a lot of the pieces together. Now, if you guys were at the seminar last time, Francis Galton was mentioned. And Carl Pearson worked with Francis Galton. So they were two of the first ones who were kind of putting all the pieces together. So this came in the late 1800s, and then we have undergrad statistics, which, believe it or not, the statistics that we study here and that are taught everywhere as undergrad were mostly developed in the 1930s. It's very new. And it's changing. Now, I've seen changes even since I was a student. Some of the things we say, we are supposed to say it a different way now because there's some issues still with some of the philosophies about, for instance, probability. So it's mostly developed in the 1930s. And Ronald Fisher is one that had a lot to do with that. We've got two paths, and it turns out the foundations of statistics are not as solid as we would like. It's a little bit like if you read the history of calculus, there was this infinitesimals. It caused a lot of issues until limits kind of came around. Statistics needs its limit. It needs something to come around. We've got these two paths. Frequentist statistics is what we study. That's what's taught everywhere in undergrad. Frequentist statistics are based on Carl Pearson, based on Ronald Fisher. But there was this other branch called Bayesian statistics, which was kind of left alone. Everybody in the 30s went with this frequent statistic path. And Bayesian statistics now are sort of making a comeback. So we're going to talk about later this guy named Nate Silver. And he runs started a website called 538, which we'll talk about a little bit. And what he says, and what a lot of the researchers say, is that they're all using more Bayesian statistics, and they'd actually like us to not even teach frequentist statistics anymore. They'd like to just completely switch. So sometimes you see Bayesian statistics, you see a little tiny piece of it in conditional probability, and then that's pretty much it. Then you don't really see it anymore. But it's a completely different. I mean, they're different from one another. But the problem is they both have some issues that are not solved yet. So it's like it's shaky, both of them. We don't have our limit definition yet, like in calculus. So there's some work to be done yet. But remember, this is a new field, right? This is new stuff from 1890. So this, is going to happen. And then the summit of the pyramid. This is just another thing that some people are pushing. Arthur Benjamin did a TED Talk. He's a professor at Harvey Mudd College, and he does he's a lightning calculator. So you may have seen him from time to time. But I heard him do this TED Talk, and he talked about what I had been reading about, that a lot of people want us to switch. So if you're in high school, all the classes kind of build up to calculus on the top. And what they want to do is switch that to probability and statistics. There's kind of a push for that, so that calculus would still be there for everybody going into the STEM fields. They need that. But the idea is, for most people who are not going into the STEM fields, just for the average citizen, they're saying that probability and statistics would probably be better to head towards that, because you have risk and reward and real-time data analysis, predicting the future, analyzing trends, things like that are better suited for statistics. So a couple of things you may see, maybe your kids, maybe when they take statistics, they'll be doing Bayesian statistics. Maybe calculus won't be the class everybody shoots for in high school. We don't know. But these are just some things that are in the works. And there's a book that I found, and it's just, I thought it was a really good book. If you have any interest in the history of statistics or history of math in general, and there's a lot of science in here, it's a very well-written book, and it's called The Lady Tasting Tea, and that is a reference to Fisher. When he did one of his first experiments, there was a woman who said that she could tell the difference if you put the creamer in first or the coffee in first. And so he set up it was like the beginning of design of experiments. It turns out that she could tell the difference. But anyway, it's a really, really good book. If you have time, I would recommend it very highly. But what I want you to do right now, we're still talking about the idea that statistics is new. If you could write on that piece of paper the name of a well-known physicist, anyone at all, first thing that pops in your mind, a well-known physicist. Usually there's a couple names, I think. So here are some physicists. These are some, this is just, it's kind of almost a a random list. I mean, I took some of the best physicists the Earth has produced, took some that you would find in a first-year stats class. I took one that's not a real physicist. Did you guys see that one? Took some that are popularizers of science. So this guy is from Big Bang Theory, right? This guy was in town 2 days ago.
Yeah, I know. I'm so sad I missed it.
Did anybody see him?
One of my buddies did it. He said it was amazing.
Yeah, he's if you get a chance to see Neil deGrasse Tyson, he's always entertaining. And he did the Cosmos, that Cosmos series. You guys see that? Who's never seen Cosmos? Here's what you should do. Your next class, you should probably just, if it's not math or science, you may want to just skip it and watch Cosmos. I'm kidding, of course. Go to class you can watch on your phone. You know. Well, you should see it. It's really good. The fact that you're here tells me you would probably like Cosmos. So, also, let's see, what else do we have? Okay, so just some names of this one. But how many of you guys have heard of at least 10? Just because I want to make a point here, by show of hands, who's heard of at least 10 of these names? Okay, who's heard of all but a few? Who's heard of all of them? Okay, so, all right, so here's the next question. I need you to write down the name of a well-known mathematician. Well-known mathematician.
Can't be Bayes.
What's that?
Can't be Bayes.
No. Anyone at all? Oh well, okay. A little quick on the trigger on that one. All right. So we've got some mathematicians here. Again, I took some of the ones that have done amazing things, some that you'll hear of in the first year or so of class, and some that you might not hear of. There's one right here. I guess he's a math version of Neil deGrasse Tyson. He's been on some of the late shows. He has a book called Love and Math, and it was a New York Times bestseller, actually. Who knows the connection between this guy and this guy? Anybody know that connection? There was Fermat's last theorem, right? Fermat's last theorem. And it was 357 years unsolved. Some of the best mathematicians trying to solve it. And finally, Andrew Wiles, I don't know, what was it, maybe 20 years ago or so? Solved it. It was from Princeton.
Is he the guy that made the mistake and then resolved?
Yeah, I think it might have been submitted twice, yeah.
He made a mistake the first time
Yeah.
and he resolved it.
So what about this list? How many of you guys have heard of at least 10 names on the list? Okay. Anybody heard of all but a few? Okay. Anybody hear of all the names? Okay. You ready for the challenging question? Write down the name of a well-known statistician. This one's a little tougher, right? It won't be tougher after this. After today, you'll have a couple of them in your pocket. So as you notice, the previous couple of lists, there were a couple of people on both the lists, but there were some ancients on both the lists. This one, not so much. This is as old as we get, right? And then there are a lot more new. So one thing you guys might be interested in is Nate Silver. He is he's born in East Lansing, actually. I think his dad taught at Michigan State. But he runs a website called 538, spelled out 538. And they do predictions there, a lot of interesting topics, and they always have a statistical approach. But Nate Silver accurately predicted the results of every state and the District of Columbia in the 2012 election. Guess what kind of statistics he uses? Bayesian. He uses Bayesian statistics, yes, to do that. Let's see, who else do we have here? We're going to look at a couple of these a little closer. Okay, here's a question. If you were at the talk last time, you heard of this guy, right? Francis Galton, pretty amazing. And then Carl Pearson was his protege. They worked together a lot. And then we've got Ronald Fisher down here. Now, I know everybody heard of at least one name on this list, although you may not think of this person as a statistician. Who have you heard of? Florence Nightingale, right? And then look at this, another Florence Nightingale. Well, this Florence Nightingale, actually her parents were so impressed by this Florence Nightingale that they named her after Florence Nightingale, and she ended up doing some pretty impressive work in statistics too, so her name is remembered. But yeah, Florence Nightingale, although she is known for nursing, she's also known for statistics. So that's what we'll take a look at here. Actually, I should mention too that if you look at the website for Nate Silver, 538, Time Magazine named him one of the 2009 top 100 most influential people. So, all right, let's take a look at a couple of these people. Just so you have, when you leave here, you'll know two statisticians fairly well. So Florence Nightingale is the first one we'll look at. And she ended up being really good at conveying complicated information. She was excellent at that. And what she did is she found that she couldn't use traditional statistics. She couldn't use tables and charts because at that time people didn't really understand statistics already. So you can sort of see in her words here, she's using the eyes. She's making these graphs. She's presenting data in a way that was easily understood, even complicated data. So to look at her a little closer, she, early age, excelled in math and science as a child. She used to organize everything, like very precise organization of seashells or whatever object she was collecting. And she ended up being the founder of modern nursing, that's as everybody knows. You know, her parents were against that. At that time, nursing was not seen as a noble profession. It was, she changed that when she went through and did all of the things that she did for nursing. It changed, but at that time, her parents were very much against it. She was a member of the Royal Statistical Society. And that wasn't something you could just go and say, hey, I want to sign up. You know, you had to do something impressive. And what she was good at is she was one of the first to use graphical representations of statistical data. And she did that because she was working, where she was working in these hospitals, she saw things that needed to be improved. And she couldn't get people to understand. So she was saying, I have this data, and they were having a hard time understanding what she was saying, so she used charts because the people who were making decisions couldn't understand the statistical data. So she just had a really unusual ability to get a lot of information in a picture and influence people's thinking. So one of those times, what she did is she wrote a statistical report about the sanitary conditions of the British hospitals during the Crimean War. And it was really bad. They had at the time, they had a mortality rate of 42.7%, which basically means out of 1,000 soldiers, in 1 year, 427 of them would die. And what she noticed was they weren't dying from their wounds, they were dying because of the horrible conditions in the hospital. So she did a statistical analysis, and she was very good, like I said, at convincing people to make changes. So when her changes were implemented, the rate dropped to 2.2%, which is 22 out of 1,000. And in addition to her, she, like I said, she was very good at displaying this data in a way that everybody would understand and made it really clear what decisions should be made. Really good at that. But she also, she was very, although like any good nurse, she's very empathetic, she was very kind, but she was a strong person, she was very smart. And if you ever look into what she did, it's amazing the changes that were made just by her suggestions. And if you're wondering like how she gets that done, here is one of the notes one of the soldiers wrote home talking about her, and this is what he said. So although she was very empathetic, very kind, she was very smart and really good at conveying information with it. Everybody understood and made it very clear, oh, it looks like we should do this, right? And then she just got a lot of things done. And she had a new sanitary science statistics departments and a lot of changes in healthcare because she suggested it. And it turns out that the English Secretary at War took her reports very seriously and basically did whatever she suggested, and a lot of changes went through because of that. So also we have Ronald Fisher, or Sir Ronald Fisher, because he was knighted. And this is the kind of thing that you hear about him all the time. That's what everybody will say when you read about a math historian or statistics historian talking about Ronald Fisher, something like that always. In fact, I'd even see things where in that era, a statistician would find something, a significant discovery would be made, and then people would say, hey, that was, you know, that's really great that you did that. We're going to be able to use this. And they would always, or a couple of them would say, it's really not a big deal. Fisher would have found it anyway, because he was just like, he was everywhere in that field. So Ronald Fisher, arguably the greatest statistician ever. There's too many accomplishments to list. The whole screen would be filled with his work. He invented experimental design, which we're actually using right now, and so far I'm still awake. Right? So this is used throughout the sciences. He was behind that. His methods were used to increase crop production, which is said to have saved thousands of lives. Did experimental design. He was actually a biologist. Richard Dawkins called him the best biologist since Charles Darwin. He was one of the founders of population genetics. So he did a lot of accomplishments in biology also. He had some problems with publishing. It turns out he had very poor eyesight. So as a child, he learned how to do math, a lot of it in his head. And he used to think in terms of geometric pictures. So when he would publish papers, the referees had a terrible time trying to interpret it, and so it would take him a long time. And even his books, he'd have a couple of books that were like landmark books in statistics and biology, but they would have to be interpreted by other statisticians and biologists before they would be well received. So he had a little bit of problems with that. He would see the solutions and it wasn't good. He was completely different. He needed Florence Nightingale on his side, so she could have explained everything. They would have been an awesome team because he came up with some great ideas but had a hard time explaining, which also ran into some problems with teaching. He was notorious for starting with a full class and ending with two or three students. But those students, he had some really good students. So a lot of people underneath him did really good research. So problems with keeping the students, but he was really good at developing certain students. And then there was a controversy. You guys have heard of Gregor Mendel, right? He did the experiments with peas, founder of the theory of genetics. Well, Fisher looked at his paper that was published in 1865, which was like a landmark paper, and he noticed that the data fit the predictions too well. In fact, he said it fit it so well that he had a p-value. Remember that p-value? A 0.00004, which means that's a probability of that actually working. He used a chi-square test, which we actually use also in statistics, and looked at the data and said that there's just no way that it fits perfect, like exactly what is predicted, perfectly fit. And he said that really there's too much variety, there's variation in everything. It should never be that perfect. But that caused some distressed geneticists, but he ended up saying that he believed that all the results were accurate, but he thinks what happened was some of the researchers who were working for Mendel, just because they kind of knew what they were supposed to get. It's easy to say then, if you know what you're supposed to get, and maybe you're looking for a green pea, you see a yellow one, and it's easy to say, well, maybe I don't think I quite did that one right, I'm going to throw that one out. So that's what his conclusion was. But it did cause some stress for some people. And then even the giants stumble. There was a 1950 paper that said that smoking tobacco causes lung cancer. Well, Fisher was actually working for some of the tobacco companies, and he loved to smoke his pipe. So he kept saying correlation does not imply causation, past the point where he should have said, well, maybe there is something to this. So even the giants can stumble. So that's kind of they always mention his big mistake. That was it. But other than that, he did some pretty amazing things. So, which leads us to what is a p-value? And this is something that these are just used in just all kinds of fields of science, especially in the social sciences. And I want us to just look at this, because if you look at any kind of research paper, if you look in there, a lot of them will say something about p-value was this, p-value was this. And I just want us to, when we leave, just kind of have a good intuition about a p-value. And I think there's an easy way to get that intuition, which we'll do right now. So a p-value is a probability. You can think of this p just meaning probability. The probability of getting a result equal to more extreme than it was actually observed, assuming that the null hypothesis is true. That's not going to make much sense until we actually do. We're going to do a quick experiment here. So it turns out the smaller the p-value, the stronger the evidence against the null hypothesis. So what we can do is we can test a coin toss. So let's say we've got got an outcome and a p-value. So with this one, let's say I've got a null hypothesis. Let's say I've got a quarter. So the null hypothesis is the coin is fair. The alternate hypothesis is the coin is not fair, meaning it's got a 50-50 chance of landing heads or tails. So see if I can do this without dropping this all over the place. So let's say I flip this coin.
Heads.
Heads. Okay, so the outcome is heads. The p-value is the probability that I could get this, given that this is true. If I have a fair coin, what's the probability that I would get heads? 50%, right? The p-value is just a probability I could get this outcome, given that this is true. That's a p-value. Okay, so let's do it again. So I have a head now.
Heads.
Heads again. So what is the probability that I could get this outcome, given that that is true? Now what's the probability? 1/4, right? We use the multiplication principle, right? Because these are independent events. Like if I get a head, it doesn't have any influence on the next coin flip, right? So now I've got 1/4, or for the decimal fans out there. Okay, let's try this again.
Heads.
Okay, is anybody ready to say, oh, I think it's definitely not, it's definitely not real. Something's wrong here. So now I've got 1/2 times 1/2 times 1/2. We've got 1/8, right? Anybody ready to say, I don't think that's a fair coin? Not yet? Not yet, okay. So you guys are looking a little skeptical, but not quite yet. Okay? Oh, wait, that's a bad one.
Heads.
Heads again. That's 1/16th, 0.0625. So remember what this is. The p-value is the probability we could get this outcome given that this is true. That's the p-value, right? Okay. Anybody ready to say, wait a minute, something's not right with that coin? Okay.
But regardless of the sequence, we always get the same value, don't we? Because we're always going to be multiplying by 1/2 no matter what.
Yeah. So what will happen, we could have a distribution, we could have a probability distribution that counts the number of heads.
Oh, okay.
So one of them would say, like, what's probably that we get, all heads out of, like 4 heads out of 4.
Okay.
So I think of it like 4 heads out of 4. So let's try one more.
Still heads.
Still heads. Okay. So we have 5 in a row. Usually about at this point. Right. 0. What is this? 1, 2, 5. So usually there's usually a cutoff point where these p-values where people right around here start saying, wait a second, something's funny about this. So it turns out usually around here, if the p-value gets to be less than 0.05, that's when usually people say if there's a 5% chance of this thing happening and it just happened, maybe this isn't quite right. How many guys think, okay, let's take a vote. Who says you're ready to reject the null hypothesis? Who's not? Who says let's do it one more time? Okay, so see, we're about at the cutoff point. It's usually in a published result, they'll start off with this. Sometimes it's 0.01. But all the p-value is a probability that you got your outcome given that this is true. That's all it is. So if we make a probability distribution for 10 coin flips, all this is the probability that, in this case, if you have 10 coin flips, on average, you could think, well, I'll probably get 5 heads, right? That'd be the peak value. Now, every once in a while, if you flip 10 coins repeatedly over and over and over, every once in a while, you get like 9 heads, right, out of 10. But not very often, which is small. In case you're wondering, to save the suspense, the alternate hypothesis was true in that case. This is a 2-headed quarter. So, but if we increase this, because what I want to do is move from discrete to continuous. We're in discrete right now. This is a discrete concept. We can have 5 heads or 6 heads, but we definitely can't have 5.174 heads, right? We're in discrete right now. So if we do this again with 25 coins, you can see this, it's real choppy. It gets less choppy. Right now I've got 25 coin flips. It's a little smoother looking. Almost looks like we could fit a curve over it. There is a curve fitted over it. Now if I remove this, what do you guys see there? It looks kind of like a normal distribution, right? So now we've got this bell-shaped curve. So we're kind of switching from continuous. That example we did is a p-value for a discrete distribution. It's a little easier to deal with because we just keep counting. Easy, we can count. With a continuous distribution, we don't have these chunks, 5, 6, 7, 8. Now we've got these little things in between. Any number on the real number line is a possible input. So we end up getting into something else where I'm going to just prepare you to see a very good-looking formula. Some of you are going to really like it. So we're switching from discrete, choppy, to continuous over here. Now, with a continuous p-value, we can't pick one point here. We're going to pick an area under the curve. So to get an area under the curve, we have that good-looking function. Some of you, when you're in Calc 2, you'll get to play with that a little bit because, yes, because Are you guys working with that one? Oh, look at the shirt. Nice. That's not true, though, but, but yeah. Yes, that is very nice. So this goes out to infinity and negative infinity. So statistics students, remind me, what is the area underneath that curve again? 1, okay. So this is the switch then. This would be a continuous distribution. So now we can't pick a number of coins. So what we do then is instead of just adding like that, we find an area under this curve. Find an area under here, which we would use calculus and integration. And think how lucky that day would be. Integrate this. But we'll probably just use the calculator or a table where somebody has already done the integration for us. So the p-value, though, is the same kind of idea. It's just the probability that that thing happened, given the null hypothesis, is true. And with that, we're all set. Thank you. And there's posters there. Make sure you guys grab a poster and hang it on your wall. So.
Kurt, I have to tell you that those of us who know you were suspicious when you flipped the coins.
The first time. Literally the first time.
The first time would have been the second one was like, yeah, okay.
I was going to go up there and make a killing with some bets. I guess I won't.
I thought he paid Nancy.
I gotta ask you something. You've been teaching here 8 or 9 years. When did you first start teaching stats?
Just a couple years ago, actually.
And so the question I have then is, obviously you like teaching it, and I talked a little bit. I know you really like teaching it. What is it about it that really draws you to it?
I like it because of all the applied problems. So there's a lot of, yeah, just like with the p-values and just testing things, and you hear a claim, and you're like, well, can we test that claim somehow? And statistics gives you some methods for that, and so there's a lot of applied problems. So that's what I've always liked about statistics. I was just afraid to get started because, as you guys know, if you're in my class, there's a million handouts, right? And those take forever to make. So that's what I was afraid of. But now that they're made, now life is good. But thanks for coming, guys. And